Today we're going to be talking about an introduction to three-phase power. And for this first lecture in this material, I'm really going to be focusing on some background information and some jargon that is widely used throughout the industry. And we're going to get into the math and the details starting on Wednesday. So most of the circuits that we have dealt with to this point could be described as a single phase system. So a single phase system consists of a source, typically a voltage source, and we are going to represent this voltage source in the frequency domain as VP angle theta V. I'm going to call this terminal here of our voltage source terminal lowercase a, this terminal down here for our voltage source lowercase n, and then over here we would have our load, which would just be some impedance ZL. I'm going to call this terminal uppercase A, this terminal uppercase N, and give me just a moment here. I'm going to subdivide this soon-to-be circuit up into three discrete parts. So on the left-hand side, we have our source, which through some network that I have yet to draw, will feed our load over here. Well, in the middle, we're going to have transmission lines. And we would represent these transmission lines by their impedance. So I'm going to call this ZW, the impedance of the transmission line that's connecting terminal lowercase a to terminal uppercase A. And we would call this the hot wire. And then down here, I'm going to have an impedance, let's call it Z sub n, where this impedance represents the contribution of the neutral wire. And this is the type of wiring that's done in homes across the United States and most industrialized countries. Okay. Well, what I'm going to draw below here is a three-phase system that's going to be very similar except for some discrete differences. So the first obvious and major difference is that there is going to be three voltage sources. So this voltage source here on top is going to supply power to the A phase. So it's going to have some voltage, which I'm again calling VP, and an angle theta A, where this will be our A terminal. Then we'll have this guy right here, VP angle theta B, where this is our B terminal, and VP angle theta C, where this is our C terminal. And so these are this is our source side of our configuration. On the right-hand side, we will once again have our load. So I'm going to call this ZLA for the A phase of our load. ZLB for the B phase of our load. This will be ZLC corresponding to the C phase of our load. And once again, we will connect our source to our load using transmission lines. So we'll have ZWA, ZWB, and ZWC. And this will be our A phase line or conductor. Our B phase line or conductor. And our C phase line or conductor. This particular type of system is what's called a three-phase, three-wire system because it does not employ a neutral conductor. There are three-phase, four-wire systems where our neutral terminal on our source side and the neutral terminal on the load side would be connected together with an additional neutral wire. But we're looking at a three-phase, three-wire system for one very distinct purpose right now. Okay. So a question that's very commonly asked is, why is three-phase power used? Why do we use three-phase systems to distribute electricity in the overwhelming majority of the modern world? And the shortest answer is simply cost. So if we look at this first system, our single-phase system, to deliver a certain amount of power to our load ZL requires us to purchase two wires, our hot wire and our neutral wire. Whereas in our three-phase system, we can deliver literally 3 times as much power as our single-phase system, only using 1.5 times the number of wires. So it is economically much more feasible to distribute power using a three-phase system. Another reason that three-phase systems are utilized is because of how well they integrate with rotating electrical machinery, like induction motors and things like that. In a balanced three-phase system, and we'll talk about what I mean by balanced here in just a little bit, but in a balanced three-phase system, a rotating electric machine like an induction motor experiences a constant amount of torque, which means the motor does not experience unnecessary vibrations, leading to a very extended lifetime for these rotating electrical machinery. In fact, here at Louisiana Tech's Power Lab, we have some rotating electrical machines that we still use for our laboratory classes and still perform research on. that predate World War II. So if you have a three-phase system where you're minimizing the vibrations, these machines will last kind of forever, at least a very, very, very long time. All right, so let's talk now about how a three-phase voltage source, this portion of our system, is realized. So three-phase voltages are supplied using a three-phase generator, which converts mechanical energy into electrical energy by way of Faraday's law of electromagnetic induction. So effectively, we're going to have a system, and I am going to vastly simplify it here for you guys. I'm going to attempt to draw this system. I'm only going to get one good circle out of the circle tool apparently, so I'm going to have to try to draw the other one. All right, so these two concentric circles here make up what is called the stator of our generator. Okay, the stator is the stationary part of our generator, and the stator has windings. So right here, we have the A phase winding on our stator, which is going to be connected to terminal lowercase a. And then directly across, so 180 degrees out of phase on this circle, we are going to have another winding. This is A. I'm going to call this A prime, and I'm going to color in our circle here in gray. And the A prime winding is tied to our neutral. "120 degrees out of phase with our A winding is our B winding. So it'll be this guy right here. I'm going to color this in blue. This winding is attached to the B phase conductor in our system. So here's neutral, here's B. Directly across from B, we have our B prime winding. And I'm drawing this in gray because it will be attached to our neutral as well. And then 120 degrees out of phase with our B winding is our C winding. I'm going to depict in red. This black, blue, red configuration is the standard wiring configuration for a low voltage three-phase AC system here in the States. Here is where our C conductor ties in. Directly across from C, we have our C prime winding. And the C prime winding is tied to our neutral conductor. So here are all of our stator connections. In the middle of this stator is what's called the rotor. And the rotor also has windings and all that kind of stuff as well, but I'm not going to draw them here because it would be overtly difficult. So instead, I'm going to represent our rotor as a permanent magnet with a north pole on top and a south pole on bottom that rotates. Let me use a different color. With some angular frequency omega. So as our rotor spins, the magnetic flux seen by each of the windings will sinusoidally oscillate. So the way that I've depicted this right now is with the north pole lined up perfectly with the A winding and the south pole lined up perfectly with the A prime winding. And so in a configuration like that, as a function of time, we would find that our A phase, if the drawing I have up here is effectively a snapshot of what's going on at t is equal to 0, then our A phase will be at its peak value. As our magnet rotates, the magnetic flux seen by the A winding is going to decrease. And when it rotates exactly 120 degrees, our B phase winding is going to be at its peak. So effectively, as the magnet rotates, we're going to have something like this. If I could draw better, give me just a second. So here's what our A phase is doing. Let's call this VAN as a function of time, where the voltage VAN is measured between the A and N terminals of our stator, 120 degrees out of phase with our signal VAN of t will be VBN of t. So let's put its peak value right here. So VBN of t will be this voltage. And then 120 degrees out of phase with VBN of t will be VCN of t. Something like this. So let me depict that on our graph. So if VAN of t serves as our reference, where we would have this, let's call it VP, so our phase voltage, I'm going to give it a subscript A, meaning very specifically the magnitude of our phase voltage A, cosine omega t, then VBN of t would be VPB cosine of omega t minus 120 degrees, and VCN of t would be VPC cosine omega t minus 240 degrees. So the B phase is lagging our A phase by 120 degrees, and the C phase is lagging our B phase by 120 degrees, okay? If all of the coils are identical in both shape and number of turns in the coils, then the magnitude of each phase voltage will be identical. So let's write that down. VPA will be equal to VPB, will be equal to VPC. And we'll typically call this VP. All right. So this configuration is what's known as a balanced three-phase generator. Now, let's talk about what it would take to unbalance a three-phase generator. It would literally require the device to be manufactured incorrectly, meaning that the windings would not be matched. It frankly does not happen. Three-phase generators do not leave the manufacturing plant unless they are balanced. So we will always, always, always be working with a balanced three-phase generator, okay? So our source is always going to be part of a balanced system, and then any imbalance is going to come about either in our transmission lines or in our load, okay? All right, so I'd like to talk to you very quickly about a concept called phase sequence now. Okay. So there are two different types of phase sequences that we might see. A positive phase sequence sometimes just shortened down to an ABC sequence, and then a negative phase sequence. Or CBA sequence. Okay. So the system that I've already described is a positive phase sequence system where we have some voltage VAN of T is equal to VP cosine omega T. Our voltage VBN of T is equal to VP cosine omega T minus 120 degrees, and VCN of T is equal to VP cosine omega T minus 240 degrees. In a negative phase sequence system, the rotor simply spins in the opposite direction. What that results in is a set of voltages where VAN of T is equal to VP cosine omega T. VBN of T is equal to VP cosine omega T plus 120 degrees. And VCN of T is equal to VP cosine omega T plus 240 degrees. So the C phase leads the B phase, which leads the A phase, okay? So this is a positive phase sequence when omega is spinning, or a positive phase sequence occurs when omega spins in a counterclockwise direction. Negative phase sequences occur when omega represents rotation in a clockwise direction. The reason why we would use a positive phase sequence versus a negative phase sequence is literally just to change the direction of rotation for our three-phase electric motor. Okay? In this class, we are going to be dealing with everything as if it were a positive phase sequence system, purely for simplicity's sake. But again, the only difference between a positive phase sequence and a negative phase sequence is the direction of rotation of our generator. Okay. All right. So this is how our three-phase voltages are physically generated. Now let's talk about our source and load configurations. So we are going to start with what's traditionally called the Y, or we sometimes literally just represent it with the letter Y. Connected source. In many textbooks, I would say the overwhelming majority of textbooks actually, a Y connected source would be represented like this. So this terminal here is going to be our A terminal. This is our B. This is our C. And then this point of interconnection between the three different sources is our neutral terminal, and it is optional, meaning that we do not actually have to connect anything to it. Okay. So what I'm going to do now is use what's called a double subscript notation to identify all of our voltages. Okay. So since this voltage source here on the left occurs between, and the positive polarity terminal is associated with the A terminal, and the negative polarity terminal is associated with the N terminal, I'm going to call this voltage VAN. And I'm going to represent it as an RMS phasor. This voltage source will then be voltage VBN, and this voltage will be VCN. Okay. So this double subscript notation simply means that the first letter of the subscript represents the positive polarity terminal of the voltage, and the second letter of the subscript represents the negative polarity terminal of the voltage. And then I'm using lowercase letters to indicate that we are on the source side of our system. Okay. So this is how a Y-connected source is typically represented. I struggle to draw this well. And so I typically represent a Y-connected source in a slightly different way. Okay. So I'm going to show you what that looks like here. So this is going to be our A terminal. This is our B. This is our C. And then down here will be my neutral. So this is our voltage VAN. This is our voltage VBN. This is our voltage VCN. And again, our neutral terminal is optional because we have this effective neutral bus on the left-hand side where all of our sources are tied together. Okay. So a three-phase source has a lot of different pieces of information that we may want to know about it. Okay. So I'm going to start by defining the concept of a phase voltage. So a phase voltage is simply the voltage drop over one phase of a source or load. So in this case, our phase voltages are simply voltages VAN, VBN, and VCN, or the voltages that are supplied by each phase of our source. These may also be called phase to neutral voltages. Phase voltages are typically more in an academic setting. Phase to neutral voltages are more of a, that terminology is used in more of an industrial setting. Then we have line voltages. where a line voltage is the voltage drop measured between transmission line terminals. Of a source or load. So let's do these in blue. The voltage difference between transmission line terminal A and transmission line terminal B is VAB, and this is an example of a line voltage. We would also have, so I'm going to be a little bit easier to see on this side, a transmission line voltage, or excuse me, a line voltage VBC, and a line voltage VCA. These are also referred to as line-to-line voltages because they are literally measured from one transmission line to another. Give me just a moment. I believe my doctor's calling me. All right, sorry about that. So these are our three line voltages. Now I'm going to introduce the concept of a phase current. Where a phase current is a current through one phase of a source or load. So I'm going to depict these in green. So this would be an example of a phase current. Because it's the current flowing through the A phase of the source, where my double subscript notation is giving me effectively the direction. So it's flowing from the A node to the N node. Similarly, I would have a phase current IBN and a phase current ICN, and I could represent all of these on my diagram here as well. So there is also a concept called a line current, okay? But we will not see a line current in a source or a load. So line currents are literally just the currents that flow through the transmission lines. So we won't actually be able to depict them until we draw a full system that contains transmission lines, okay? So these are our Y-connected voltage sources. and where all of our phase voltages, line voltages, and phase currents are found. Okay. So before we move along to the next type of voltage source configuration, does anybody have any questions about any of this? All right. Now we are going to talk about, it's called the delta connected source. Okay, so Mr. LeBlanc has asked, why do the phase currents flow into the positive terminal? And the short answer is literally just because I said so. So I am defining them in that way for the sake of consistency. Let me scroll up here. Okay. So I'm using a double subscript notation where wherever the current starts is the first letter in the subscript, and wherever the current ends is the second letter in the subscript. And in doing so, that means that the current is going to be flowing into the positive polarity terminal of our source, okay? I'm doing this to be consistent with the way that we are defining positive polarity and negative polarity for our voltages as well, right? So I would find it overtly confusing to have phase voltages, VAN, but phase currents, INA. Does that make sense? Because I would need to change the order of my subscripts in order to change the direction of my current. All right. So I agree that for sources, this does seem awkward because effectively we're looking at it from a position of absorbed power. But for consistency's sake is the reason why I'm doing it this way. And when we're looking on the load side of everything, we'll be looking at, or even in the load side and the transmission line side of everything, this particular configuration will give us the absorbed powers that we're looking for. So. All right, so delta connected source. Once again, there is a way that these are traditionally drawn in textbooks that I struggle with. So I'm going to introduce the textbook version first and then how I typically represent them. Okay. So this is going to be my B terminal. Here is going to be my A terminal. This guy is going to be my C terminal. So using our double subscript notation, this is going to be VAB. This will be VBC, and this will be VCA. So this is the traditional drawing, which again, I know that I'm very bad at, don't like doing it. One thing to point out here though, that is interesting is that there is literally no neutral connection whatsoever. The way that I prefer to draw this configuration looks like this. So here's my A terminal, my B terminal, and my C terminal, which gives me a voltage here, VAB, a voltage here, VBC, and a voltage here, VCA. So our definitions for phase voltages, line voltages, and phase currents do not change. So a phase is the voltage drop over one phase of our source in this case, which means our phase voltages are simply VAB, VBC, and VCA. Our line voltages, let me go back here and see what color I used, blue, will be VAB, VBC, and VCA. We can see probably a little bit more obviously that these are literally the exact same thing as our phase voltages. Okay. So this is where things start to get a little confusing, which is why I spend an entire lecture period talking about this jargon. So for a Y-connected source, the phase voltages and the line voltages represent different information, whereas in a delta-connected source, the phase voltage and the line voltages represent the exact same information, which is why the terminology of phase to neutral gets used a lot when talking about Y-connected voltages, and the terminology line to line voltages gets used a lot when talking about delta connected voltage source, because there is no possibility of misinterpretation. Okay. Now we'll talk about our phase currents. So our phase currents are simply the currents flowing through one phase of our source. So here we're going to have phase current IAB. This is phase current IBC. And this is phase current ICA. And let me see if I can sneak them in here. IAB, IBC, and ICA. So these are our delta connected sources and the kind of signals of interest that we may be asked to find when we're analyzing these types of circuits. Does anybody have any questions regarding our delta connected source before we move along? All right. So Those are the only two possibilities for us to connect our three-phase sources. We will always have either a Y-connected source or a delta-connected source. Those are also the only two different ways that we can connect loads in a three-phase system. So we will either have Y-connected loads or delta-connected loads. So let's look at our Y connection first. So this will be my A terminal. I'm going to call this impedance ZYA. And then here is my neutral. Notice that since I am on the load side of the system, I'm using capital letters to designate things. This guy right here. This is looking worse than usual. Is going to be ZYB. Here we have ZYC. And now I'm going to draw my easier, at least for me to draw, representation, which is going to look something like this. So here's the A terminal. ZYA. Here's our B terminal. ZYB. Here's our C terminal. ZYC. And here is our neutral terminal. And we can also think of this whole back bus as a neutral as well. So our phase voltages are going to be VAN, VBN, and VCN. And these are the exact same thing as the phase voltages on the source side, but we use capital letters because we are on the load side. Then we're going to have line voltages. So here I'll just depict VAB. On this side, I'll do all three of them because it'll be a little easier for me to do. So here's VAB, here's VBC, here is VCA. Then we have our phase currents. Which by definition are the currents flowing through our the different phases of our load. So this is going to be IAN, IBN, ICN, or here. So those are our Y connected voltages and our potential signals of interest. And then the last thing that I want to talk about today is the delta connected load. So our delta connected load is going to look something like this. So I'm going to call this Z delta A. And it is between the A and B terminals of my load. Z delta B connected between the B and C terminals. And then I have Z delta C connected between the C and A terminals. Drawing this in my arguably simplified form. We have Z delta A Z delta B and Z delta C. For these delta connected loads, we are going to have the following phase voltages. Once again, these are going to be identical to the phase voltages of a delta connected source. We just use capital letters. So we're going to have VAB, VBC, VCA. Our line voltages are going to be the exact same thing. VAB, VBC, and that B looks suspiciously like an A, so let me rewrite it. And finally, we have our phase currents. IAB, IBC, VA, IAB, IBC, ICA. All right. So that's the last thing that I want to talk about today. We are going to kick things off with on Wednesday is we are going to describe a full system. We are going to start with what's called a Y-Y system, wherein we have a Y-connected source and a Y-connected load. We are going to introduce the concept of line currents, and then we're going to do some analysis in a general sense to see what happens when we have a balanced system and what simplifications that we can make. The analysis that we're going to be doing could be applicable to any system, but very specifically under balanced conditions. We will develop a means by which to vastly simplify a circuit. And then we are going to introduce a number of transformations that we can use for our further analysis. All right, so unless anybody has any questions, I will see you all on Wednesday.